Hi, good morning, everyone. Let's go ahead and get started. So first of all, I see a question in the chat. Is there a specific tutorial for ggplot2? Um, yeah, so I think that in some of um, the, the the R notes that I posted in the files for some of the lectures should have a link to it, but I can post it in the announcement so it's a little bit easier to find. Yeah. Okay. So before we start today, I did want to quickly talk about the 289 final project. Some folks have been asking, so we'll start to provide a little bit of information about how to get started, what to think about, and some of the minor deliverables for the project. Okay, so the project I think is a pretty good opportunity to apply what you've learned and will learn in this class. I think that application of the material that we have in this class through the project is the thing that will sort of best help to translate into learning about how to do this for your own research efforts. And sort of along the same lines, I definitely encourage you to relate your data analysis either directly to your research or have it as a piece that could be extended into research in the future. Should be something that you're interested in, and it 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 doesn't have to be there's no like topical requirements as long as you find sort of a data set and enough to do analysis with it and it being interesting to you, then that's what you can do. To make sure that folks are kind of on track, I'm going to have a couple deliverables so that you can start to think about this ahead of time. So we'll have a project proposal, which will be due at the beginning of May, and then the presentations. So those are going to be, I think I have them scheduled during finals week, but we could also do them the week before, depending on what people are feeling. The last week of classes, if you look on the syllabus, is actually just dedicated to folks working on their projects, and I'm more than happy to help out during that time as well. The final project report will be due at the end of finals week, which I believe is June 13th. Oh, and I should mention that the project presentations, all the presentations are going to be due on the first day of presentation so that everyone has kind of a level playing field in terms of during the presentations, because there's enough folks that will need to do it over 2 days, so everything will be due on the first day. For the project proposal, this will be kind of a short one-page summary. Oh wait, okay, so comment June 13th is a Saturday. I probably meant June 12th. I think I was thinking that this class was on Monday, Wednesday, and I added 2 instead of adding 1. So June 12th. I'll edit that so that everyone will have the right reference date. Unless you like really want 1 extra day and want to work on Saturday, but I imagine that you don't. So we'll just make the due date on Friday of finals week. For the project proposal, it's just a short sort of 1-pager describing the data set. So what's the size of the data? Where are you getting from? Maybe some summary statistics, identifying the names of columns in the data, maybe a description of each field. And this is more for me to help gauge whether the data set is adequate for the purposes of doing a class project. And I can certainly provide feedback and help point out to potential data sets for people who are looking as well. And then also thinking about how you might want to approach it, what things you're thinking about looking at, what hypotheses do you have. And again, this is for me to provide feedback, to judge whether or not the scoping of what you'd like to do is enough for the class or too ambitious for the class. We want to get in kind of this sweet spot. And don't worry about it being kind of preliminary. It's more than likely that your hypotheses may change, especially after providing feedback. So the project presentation, 10 to 15-minute presentation. What did you learn from the data? Interesting overview of the data, and then doing presenting results from the actual analysis, doing regression or unsupervised learning, basically showing the application of some of the stuff that we'll be covering in the course into your analysis. Project report. So it's don't worry too much about the length, but make sure to essentially talk about the process. And this isn't, I think, it's not only going to be about the final product. You should also talk about things that you did to manipulate the data cleaning and parsing, thinking about summarizing the data and how that sort of helped form your hypotheses and your ultimate approach, and then talking about again sort of the process of your analysis. Did things turn out as expected? How does it relate to your hypotheses? And so employ, again, what we're learning in class. You're not going to do sort of every sort of technique that we cover, but if it's relevant to the data analysis that you're doing, then you should definitely make sure to include it. One other thing, for the projects, you are allowed to work in up to groups of 2 people. So if you want to partner up with someone, that's totally fine. Of course, the expectations for a single-person project versus a 2-person project is obviously going to be slightly different, and so you can keep that in mind as we move forward. And I know that this quarter in particular will be slightly more challenging because it's unlikely that you're going to be able to do face-to-face meetings. But hopefully, if you do partner up, you'll still be able to work it out with online meetings. Okay, so that is the basic overview of the projects. Does anyone have any questions about that? Okay, barring any further questions, just one quick logistical information for the class. So the first homework is due today at the end of the day. And again, just to reiterate, please make sure, so you can submit your source files and everything, your R code, but the thing that I'll be grading should be just one PDF or HTML document for and it should be in the R Markdown format or Python notebook type of format, so either in Jupyter or IPython or something equivalent, or a single PDF LaTeX compiled file. Okay. So barring any questions, let's go ahead and, oh, okay, I do see a question. Okay, so actually some people have been asking about this. So for the table in problem 1, how to submit it, you can either create the table in R, or yeah, you can either create the table in R and include it in the Markdown file, or you can, if you're doing it in LaTeX, you can make a LaTeX table, or if you are doing it by hand, you could write it out and then include it as a PDF in your R Markdown or in your LaTeX file.
Hey, Alan, I don't know if this is annoying, but can we turn it in as an HTML from?
Yes.
No? Okay.
Yeah, and I think I have that already listed as one of the formats in the assignment, so you should be able to submit it. If not, just let me know.
Okay.
Shouldn't be a problem. Couple more questions popping up. Okay, there's a question about how we know we've created an R Markdown as opposed to separate codes. Okay, so so the R Markdown is something that you can put together in RStudio. Let's see, I don't think I ever actually went through exactly how you go about doing that. Okay, so really quickly, an R Markdown file is essentially a way of creating a document that lets you sort of tie together commentary and code all into one place. It's pretty simple to do. They're pretty straightforward, at least to initially set up. And I'm not going to show how to do that here, but after class, what I'll do for folks who aren't familiar is I can post an example of an R Markdown file just so that you can see the general format. Okay. I see a pretty specific question from Vishnu. Why don't we talk about that at the end of today's class? Okay.
Sorry, Alan, one more question about the homework.
Yes, go ahead.
For the true false table, is it okay if we had Python or R do all the work for us in like figuring out that logic, or do you want us to have thought through it?
Yeah, a couple of people have asked me this, and I probably should have worded it better. At this point, it's okay if you just have the program do it for you. Although I was sort of intending for people to think about the logic and sort of work through it by hand. But at this point, it's okay to just have the code do it for you, and hopefully at the very least, you should be familiar with what it's doing. So yeah, I'll leave it at that. I honestly, I wouldn't be able to tell if you did it anyways, because you could just
check it,
write it in code, and then write it down by hand afterwards. So, it's more to get yourself familiar with the logic tables and how they work, because it comes in. A lot of that logic comes in handy when you're doing data analysis.
Cool. Thanks.
Mm-hmm. Okay. Good. I think that is all the questions for now. So let's move on to today's lecture. So actually, I'm going to start with answering a question from last lecture that was talking about the residuals. And the question was about whether or not we can plot the residuals against the x values, so the explanatory variables, rather than just the fitted term. And the answer is yes. So it'll provide you a similar set of information as the residuals against the fit, and in fact, for a univariate, it will provide you the exact same information. And as you go into sort of multivariate models, it can be handy to look at the residuals against the explanatory variables, to see if there are any patterns particular with specific variables, which let you identify some things where you may have correlation with the error term, and that can actually be apparently a sort of diagnostic tool, one that I actually haven't been so familiar with and used in the past, but it is one type of thing that you can do. I also do want to clear up any potential confusion in plotting the residuals. So it is really important to make sure that when you plot the residuals, that you are looking at y hat and not y. And the reason for this is actually that there will almost always be a non-random pattern when you're looking at a plot of the residuals against the y, and we can quickly see why this is, right? Okay, so here, if you had something like this in a linear model where you have your residuals sort of randomly scattered about, in a true sort of linear model, you're almost always going to have some kind of clear pattern if you plot against y. So if we look at our equation, in the prediction world where you're looking at the y hats, this is your equation. So every x value multiplied against the slope has some corresponding y, which lies along the line. Okay, but in your true model, there is always some correlation between your yi and your error term. So your residuals up here are always going to be non-random, unless you actually have a really bad model. And so one thing to keep straight in your mind is to make sure when you're doing the residual plots that you're comparing against the fit of y and not of the raw values of y. And there actually is some formal proof to demonstrate this, but we don't need to dive into that. Okay. So one of the things that we're going to start off with is continuing thinking about or building in sort of layers of complexity in our linear model. And so one of the first things I want to talk about was interpreting. Oftentimes you'll see the log of, or when I'm saying log in this case, so oops, let me switch back to black. So log is, every time I say log in this class, it's referring to the natural log, not base 10. Okay, so everything we've talked about so far is sort of in this form. So y is equal to alpha plus beta x plus epsilon. And this type of model is called level. And as we do an interpretation of this, the change in y is equal to beta times your change in x, right? And so the interpretation of this model on the left is as x increases by 1, then y will increase by beta, okay? So this is thinking about essentially applying your slope and looking at how it influences your response variable. So x increments by a unit value, which means y increase by that unit value times beta. It's pretty common to have some sort of transformation. And so when we think about applying a linear regression to a set of data, you want the relationship between the parameters to be linear. And so if there is a exponential relationship of any kind between your x and your y, which is typically a lot more common. So when we're thinking about real world data, linear relationships are probably far and few between, like real linear relationships, whereas exponential type of relationships are really commonly seen, and so it's not at all uncommon to do a transformation using a log to turn your x's or your y's into linear relationships with each other. And so we'll take a look at how to interpret some of those types of models. And if you're not quite following, just to give a sort of quick qualitative example, suppose we have something that looks like this. and sort of extra data, right? So this would be a, you would have an exponential sort of growth that looks like this. If we were to apply a linear relationship between this, you may end up getting like a line like that, whereas really what you want is the black line. And so you can transform this into a linear set of points, so it looks something more like this, by taking the log of y. So the whole idea of these transformations is basically to get a linear relationship between your explanatory variable and your response variable. You're essentially linearizing it. Okay. So as we do that, that transformation is interpreted slightly differently. And so we call that type of model log level, where you are doing log of y, which is equal to, let's say, again, same type of structure, beta x plus epsilon. And in this case, essentially, the interpretation here would be a percent change in y is equal to 100 times beta delta x. So as x increases by 1, y increases by 100 times beta percent. Okay, and so now what ends up happening is that unit changes in x are leading to percent changes in y. And the reason for this type of interpretation, it's okay. So it's pretty common, and some of you who have done this type of regression before, maybe a little bit more familiar, or are already familiar with this concept that you can do sort of percent changes. But the actual reasoning behind this is that, so what is the log of 1? Does anyone know? So, okay, the log of 1 is 0, and the log of 1.01 is approximately 0.00995. So it's about 0.01. And so this is kind of the mathematical justification behind being able to do an interpretation like this, right? Because what we're essentially saying is that unit changes in x are leading to approximately percent, or one 100th changes in y, which is most commonly sort of interpreted as percent changes. But make sure that you understand that this type of interpretation is coming from a mathematical approximation. So this makes the most sense sort of at the margin. So if you're doing small changes in x, then it'll be fairly accurate. But if you are doing really large changes in x, then your approximation for how the percent changes in y are happening are going to be increasingly inaccurate. So one thing to keep in mind, but generally that doesn't come up too often, and most people sort of just accept this relationship. Okay, we also have level log, and this is where y is equal to alpha plus beta times log of x. In a similar manner of linearizing your y, you can also be linearizing your x. And in this case, it's pretty similar interpretation, right? So delta y is equal to beta divided by 100% times delta x. And so as x increases by 1%, y increases by beta over 100. And so this is kind of the converse of what we were saying in the log level one. Now you increase the marginal value of your explanatory variable by percentage, and it creates unit changes in y. Okay, and the last one, you guessed it, log. So this would be log of y is equal to alpha plus beta log x. And in this case, you'll have something like percent change in y is equal to beta percent change in x. So as x increases by 1%, y increases by beta percent. And this is most common to, or this is really common in econometrics and economic-based regression analysis, where you're deriving like elasticities, for example, because that's actually exactly what you want to be displaying in an elasticity, sort of percent change over percent change. So that might be something like, if I had like VMT is a function, if ln of VMT is a function of ln gas prices, then the interpretation of this would be the elasticity of VMT with respect to gas prices is beta, right? And so as gas prices increase by 1%, then VMT will change by beta. So that's just a practical example of the log. Okay, question. So in the last one is called elasticity. Do the other ones have corresponding terms? No, they don't. Or at least not that I know of. It's not uncommon to have those types of interpretations, but it's just sort of convenient that the log one happens to essentially measure the elasticity term that folks are pretty interested in. So there just happens to be a specific term for that. Okay. let's move on. So we're going to shift topics a little bit here. We're going to talk now about outlier analysis and thinking about going back to the basic tool set of our modeling approach. One thing that you'll need to keep in mind is how to identify outliers, and then I will talk a little bit at the end of this to think about what you should do with outliers, and in fact, a lot of data analysis and application of identifying outliers isn't something that I do so much. There are different schools of thoughts about how to approach outliers and whether you should include them or exclude them. And I'm sort of more in the camp that you keep all the data in your data set unless there's like a very specific reason not to have it there. But there are others who will advocate that you sort of have a careful treatment of the outliers. But either way, I think learning about how to identify them through specific statistical methods is a useful tool to have. Okay, so let's dive right in. Outlier analysis. So we're going to talk about basically a couple metrics to do this identification. Okay, so the first is known as leverage. So this is how much would a predicted value change if the observation was shifted 1 unit in 1 unit in the y direction. Okay, so the formal sort of definition of this is HII is equal to the delta of your predicted value over your delta of your actual value. Okay, so essentially what this is doing is, suppose we have a whole bunch of set of points, and we've got our x's and our y's here. And you've got a your best fit line, linear line through your cloud of data points. What the leverage is going to do is shift an individual point from here to here, and then it'll observe essentially how your line changes. And so this is a ratio, which means always between 0 and 1. And so it will return a leverage point for every point in your data set. And typically, kind of a rough rule of thumb is that the cutoff is usually 0.2, about 0.2, although there's some wiggle room here depending on your particular data sets and your sort of personal threshold for what you consider to be an outlier or not. Okay, so the basic concept, and we'll show how to actually execute this in R in a little bit. But again, the basic concept here is that the x's that are sort of really far out, that are outliers. So say we have something up here, as that increases, as you perturb that point upwards, it's going to have a stronger, it's going to have a stronger effect. Okay, wait, hang on. I'm confusing myself with the influence one that we're going to talk about. It's not when it's far out on X. It's when it's far out, or not far out on Y. It's when it's far out on X. You can actually, this is the principle of this is kind of like torque, right? And so the farther out along the x-axis for your explanatory variable, as you shift these ones, it's going to have a much larger influence than x's that are closer to the center, right? You can see that essentially the farther out along the boundaries of your explanatory variable you are, the stronger effect it's going to have on playing a role in influencing the general fit of the model. So let me just write this. So this is generally good for identifying outliers along X. Okay.
Alan, can I ask a question?
Yeah.
So in the formula for calculating H sub II, is the change in the predicted value y hat I over the change of the observed value yi? So in your example where you perturbed the x's, or like the data points, that would be considering moving like yi. Is that correct?
Yes, that's right. And so essentially, so let me see, I'll use different colors. So this is the yi perturbation. Okay, and then if I go like this, and we'll sort of continue out to here so that it's along the same place. Although should be in the other direction. Sorry. It's gonna bring it down. So this is delta yi hat, right?
Right.
Because you've shifted the line down to here.
Right.
And the ratio of how the predicted changes with the delta is going to be mainly what you're interested in.
Okay, thank you.
Mm-hmm. Okay, so there's this question. So if h is greater than 0.2, we might want to drop the observation. Okay, and so I haven't said anything about what you should do with the outlier, but this is where some of the like art comes into play. So right now we're just talking about like strictly, you know, statistical definitions for how you might identify an outlier. And then in terms of what you actually do with the outlier, it's kind of up to you, right? So, you know, I might be just identifying the outliers for the purposes of saying, okay, look, I've run this model, and here are my here's my, you know, coefficients and my interpretation of the model. But I might say something like, oh, but note that, you know, this coefficient may be somewhat influenced by the presence of outliers that we've identified. That's, you know, one sort of approach versus, oh, we eliminate the outlier and then we run the model, and here are the results, right? So just because it's an outlier doesn't mean that you should just drop it from the data set. And in fact, I'm not saying that this is kind of the correct thing to do. And in fact, you know, people will differ on their opinions about how to treat outliers. But I was sort of trained to basically keep all the data in your analysis, because, you know, it's you at the point where you start to be selective about dropping outliers, you are taking it upon yourself to create criteria for inclusion of data points, and that can be slightly sort of arbitrary, right? Because like the h of 0.2 is like a totally arbitrary sort of cutoff point, and it's just kind of this general rule of thumb. And so, is it fair to cut them off at like 0.19, so on and so forth? It's kind of a slippery slope, but you know, some people would argue otherwise. So I'm not saying that that's necessarily the right thing to do, and I will personally kind of just leave it up to you guys in terms of whether you think it makes sense to keep the outliers or not. Okay. The other type of outlier is called influence. And this is a different way of measuring how important a point is. So this is the effect of deleting the point. And I should also mention this is sometimes also referred to, you may see this as Cook's distance. So you could imagine that if I have a whole set of points like this, and I were to, okay, and so the best fit looks something like this. If I were to delete, let's say, this point, that may shift my fit line up a little bit, right? And that's going to have some sort of effect. And so here, the Cook's distance is the one that's good for identifying outliers in the y direction. So similarly, I'll write the equation, but again, just for your reference, you won't need to memorize this or anything. And you know, for a lot of the stuff that we're doing, which is less proof and theory based, it's more implementation. It's just about running the code, right? And so there's functions that will do this for you, so you don't need to worry so much about it. But I will include this just sort of for your reference. So di the Cook's distance. So you're going to have a Cook's distance for each point in your data. So I see a question, isn't there a method called jackknife that's similar to that? So yeah, I don't want to say anything about that. I think you're right, but I don't have it clear in my mind exactly what jackknife is, but I can look into that and get back to you. I think if what I have in my mind is correct, I think that the jackknife method is like a similar type of procedure, but it's for a different application. But let me check that and get back to you. Okay, so this is the sum of j. Looks something like this, divided by p times r mean squared error. So this is, the p is the number of coefficients. Sometimes you'll see that as k, and in fact, I think I've referred to it as k in previous lectures, but for some reason, a lot of the definitions of Cook's distances usually have j. And then let's take a look here, and then our squared value, or sorry, not this squared, the j value is so this term here is the fit without yi. So there are two yi fits, so this one, and the one on the left is the fit of the overall model, and the one on the right is the fit of the model after you've dropped the one point that you're interested in. So this is the sort of formal definition of Cook's distance, but as long as you have sort of the interpretation of the chart and the graph on the left and what's happening. So you drop a point, you look at the change in the predicted value of your y. That's the general concept of Cook's distance. Okay, so the next thing we're going to do is actually to show how to implement this in the code, but we are about halfway through the class, so let's take a break before we jump into that. So we'll do 5 minutes. Let's reconvene at about 11:04. Yeah, you can grab some water, use the bathroom, and in the meantime, I will be here for questions.
Hey, Alan, I have a question about the homework real quick.
Yeah.
So for problem 2 at the end, you ask us to write a function that will take any integer input and sum the digits together.
Yep.
I was able to do that, I think, with a string, but I wasn't quite sure how to do it with a modulus operator.
Yeah.
It point me in the right direction.
Yes. Sure. So I will say, first of all, that you don't have to do it both ways, but you do get a little bonus if you do it both ways. So for the modulus operator, here is so to get you started in thinking about how to do that. I helped some other people with this as well. So let's suppose we have the number 1, 2, 3, 4, 5, 6, right? And so if we so the thing that we want to get out of this is 1 plus 2 plus 3 plus 4 plus 5 plus 6, and that's our answer. So I want to be able to do something to this number and return 1, and then I want to do something to this number to be able to return 2 and 3 and so on and so forth. And I want to be able to generalize that for any number. Okay, so let's take a look.
Actually, before you start, can I ask you a simpler question?
Yeah, sure.
So, I mean, the way I wrote it was with as numeric unlist. So I think I did break it up into different characters and then count them.
Yep.
Is that considered a modulus or is that considered a string?
That's considered a string.
Okay.
Yeah. So let me ask you how might I return just the number 6 here out of all of this?
I mean, you could make that in like use C and make it into a vector and then call for the last one.
So yeah, but that's but that would be going along the same route as your string thing. So think about modulus. How would I divide? What would I divide this number by so that I have a remainder of 6?
Oh, okay.
Yeah, see it in the chat. So it's 10, right? And so if I divide this number by 10, it'll be 12,345 with a remainder 6, right?
Okay, yeah.
So that is going to give you 6. Okay. What about this? What will this return?
5.
5, right? And then so on and so forth.
Okay.
So that's kind of my hint to you about how you would go about doing this, right? I can go from this step to this. The other thing that you would need to know is the floor function, which is rounding essentially. So it rounds down. So if this is how I get 6, then that's kind of step 1. Step 2 is to be able to get 5, and to make 5, I have to go from this number to this number.
Mm-hmm.
So if I were to do 1, 2, 3, 4, 5, 6 divided by 10, and I round it, that would give me that, right?
Okay.
And so on. Right, I can do this to extract all those numbers. So you have to just design the function in such a way that I could take advantage of these operations and tools to get me what I want.
Okay. That helps.
Yeah. Facundo's asking, is as integer the same as floor? So no, it's not. Functionally, it might be similar. Actually not sure how as integer will do any rounding. So if I do 5.6, does it round down? Yeah, it does. So for some purposes you can do that, but you also have to know that you're transforming a numeric into an integer, which in this case may not make so much of a difference, but it potentially could be doing something that you don't intend it to do. For example, let's see. Does this transform it back into numeric? Let me do that. Yeah, it does. So it's, I guess I'll say it's functionally the same, except it transforms your numeric into an integer, whereas a floor keeps it as a numeric. And whether or not that makes a difference depends on the context. Okay, that was a quick break. Let's go back to the lecture material and think about the application of the outliers into our code. So I'm going to start off again using our typical regression data set that I've been sort of drawing on in the past couple lectures. So in talking with a couple of the students in the class, you know, in office hours or in separate meetings, there is a sort of balance that I have to make in showing this code to the class, because there are some folks who are pretty familiar with it and some folks who are just learning R, and so this is going to be really fast for some people and it's going to be kind of slow for others. And so as I work through this, for those who need more time to catch up, please do sort of make sure to review this code. All of this in class coding I put up on Canvas, and so you should be able to review everything to understand what's going on. And you know, this particular thing that I'm doing right here, I've done this in a couple lectures. So if you're not understanding the code at this point, please do make sure to review the code yourself to make sure you understand what's going on. So here, again, we are creating our regression data set where we're making an artificial y, which is x times 0.5 plus our deviation. And then what we're going to do here, so I can just show what this looks like really quick. So here's our x's and y's. And what I'm going to do to this data that we've already seen a couple times is I'm going to add a single outlier. So I'm going to redefine my x as x, but I'm also going to include a new x point at 100, and I'm going to redefine y as my previous vector of y, and I'm going to tag in another point at 20. Okay, and so if I plot this again, we should be able to see immediately in this plot the difference as I include the outlier. Okay, so we have this guy way out here at 120, at x equals 100 and y equals 20. So we'll take a look at this. And we can create a model regressing y on x. And if we look at the summary, we can see that this outlier has a pretty big influence, right? We know that the true relationship between our x and y is 0.5, whereas here it's estimating the relationship to be at 0.4. And so it's pretty obvious in this case because we have this outlier, but suppose, you know, you're in multi-dimensional space or something and it's hard to identify the point or you can't see it visually. These tools that we've talked about with the leverage and influence are really going to sort of help to create a sort of robust standard way of identifying the outliers. So the leverage, the way that you identify the leverage from the model is something like this. Okay, and so let's take a look at what this looks like. So as I mentioned before, every point in the data set is going to have some associated leverage point, right? Leverage is HII, so every point actually has a value for the leverage. And as that value is above some sort of cutoff, so I think we were saying generally the rule of thumb is 0.2, we can see that it's fairly different from the rest of the points. And so that's an easy sort of way of being able to quickly sort of jump out and identify your outliers. Some people like to plot your x's against your leverage, and so you can see sort of just across the different values of x's, which ones jump out really far in terms of the leverage, and this you can actually see this effect that I was talking about as sort of related to torque, right? So as you're further away from the center point of your data, it's going to have a larger effect on y. So even in the case where, let me see, if I were to have a bunch of points and a line that goes through them, my x that, even if I have x's that lay exactly on the line, these points are going to have more leverage than the ones in the middle, and you can kind of see that relationship happening right here, right? The ones at the ends have more leverage than the ones in the middle. So that'll be one thing to keep in mind as you do this, as you look at leverages, is that there is some sort of bias towards points at the end. Okay. So that is our example of identifying outliers through leverage. Let's look at a influence / Cook's distance example. So this one's pretty straightforward as well. There's actually a function literally called Cook's.distance, which will get those points for you. So if I go ahead and run this, these are all your Cook's distances for each of the 101 points that we have in our data. And so I can plot this and be able to see what happens. Okay, and here the Cook's distance is quite different from all your other points. And so that's something you might classify as an outlier. I will, I didn't mention this before, but whereas leverage is always between 0 and 1 because it's a ratio between the fits, the Cook's distance is not. And the Cook's distance is actually going to depend on the particular circumstances of your model and data. And so this scale is not standardized in any way. You really have to be able to look at the relative differences in the Cook's distance for individual points to be able to identify the outliers. Okay. Any questions about that?
I have a question about identifying the outlier. And like, for example, in this case, like the model we built ourselves and we know exactly which data point is the outlier.
Mm-hmm.
But let's say it's a data set and then we run like either Cook's or leverage and we find a point which has either like past the threshold of 0.2 in the leverage case,
Mm-hmm.
or it's like way off the chart in the Cook's distance case. Like, how do we then go back and actually pinpoint that data point?
Oh, I see your question. Yeah, so there's a couple different ways you could do it. Let's see. Actually, the most straightforward way is that if you identify the leverage point, you can get it's always lines up by the same index. So if it's the 50th point, you know that it's the same one in your data set. So you can always refer to that. It's always in the same order. So you can always go back to check it that way. You can here, you can plot it against the X and the Y as a way of manually identifying the X-Y combination. But I think generally it's the easiest way is just to identify the index point and go back and identify that in your original data.
Gotcha. Index point based off of X, correct?
Yeah, X or Y. I mean either one.
Okay, thank you.
Yeah. Yep. Okay. Any other questions? Okay, so moving on to the next topic, we've sort of started out looking at a simplified world of data analysis where we are looking at this one explanatory variable, doing the interpretation, doing a little bit of diagnostics, including the R-squared, standard errors, mean squared error, and then doing outlier identification. So hopefully what we've covered so far isn't going to be about you memorizing any particular way of obtaining any of the diagnostics that we've been doing. So like the R-squared, for example, it's more about understanding and being able to interpret qualitatively what they mean, so that when we move forward to do real data analysis in a applied setting, you are comfortable with being able to apply these tools and understand what they're doing, rather than sort of just knowing the math behind them, which can also be important, but we'll leave for other classes to teach you that. And so here we're going to move on and sort of expand our worldview little by little, And the first thing we're going to expand on is now moving on from our univariate model to a multivariate model. And so this would be a regression with multiple variables. And so where we were doing something like, y equals beta 1 x1 plus your error term. Now we're going to expand to think about what happens when we have multiple variables. So beta 1 x1, beta 2 x2, and so on and so forth, all the way to beta n xn plus your error term. Okay. So the nice thing about that is that actually, for most of the stuff that that we talked about in terms of diagnostic tools, like the R squared, the standard errors, the mean squared error, none of that actually changes in any way as you go from a univariate to a multivariate model. So let's go ahead and actually start in R and think about how to code and do interpretation using the tools that we've already sort of covered in R. So the first thing we're going to do is to create a new make-believe data set, and except this time we're going to, actually I'll just save some time here. So this time we're going to have a couple different variables to look at. And so here we're doing the same thing where we're going 100 points from a random uniform distribution. So x1, x2, x3, x4, they're going to be slightly different. X1 and x3 are between 0 and 50, and x2 and x4 are between 0 and 100. And obviously the random draws are going to make them different. And then we're going to have a deviation, which is essentially our random error term that we're also going to be introducing into this model. So our y in our multivariate regression, y dot multi, is going to be equal to, so this is our formal model. So this would be, y is equal to beta 1 x1, oops, didn't mean to do that. Beta 1 x1 plus beta 2 x2 plus our error term, where the true value is equal to 0.5 like before, and now we have a beta 2 which is equal to 2 in this case. So that's what this line is describing. And let's go ahead, run that, and we're going to plot this. So again, I know I'm using the base version of plotting here, which I haven't covered, but again, don't worry too much about this portion of the code. This is just for being able to do quick visualization. I'll actually go ahead and modify this when I post it so that we can be as comfortable as possible with ggplot. So I'll actually change this into the ggplot version of the plots before I put them up. Okay, man, I really hate this viewer. Here, let's do it like that. Okay. Here we can see the relationship. I'm graphing the relationship between my x's and my y's, and so I actually know for certain that there is a real relationship between x1 and x2, right? Because this is my sort of known function, and my y's. And you can actually see the relationship between x2 and your y here. So why is it that we can't see the relationship between your x and y in this case? Even though we know that x1 is specifically leading to an outcome in y. Can anyone venture a guess? I'll take your silence as indication. Maybe it's not so clear. So what the reason for this is that you have multiple things that are influencing your y outcome, and it's just so happens in this particular example that x2 is, right, it's 2 times x2 and only 0.5 times x1. So when we think about the relative magnitude of the effect, x2 in this case is kind of swamping out the effect of x1. It's 4 times bigger, and so x2 is also random, and so that randomness is outweighing the sort of direct relationship that we're seeing between x1 and y. Okay, so hopefully that explanation is clear, but it actually sort of drives at something that's a little bit deeper, right? Which is when we do data analysis, it's always a really good idea to look at initial sort of relationships between your explanatory variables and your response variables. You want to get a sense of how they are related in a direct way. And so even before you do analysis, again, it's always really good practice to basically dive into your data, do some exploration, plot things against each other, and see what the relationships are. But right, there's a caveat here where in some cases it's like really clear, but in other cases it may be less so. And that's even knowing that there is a relationship between our x1 and our response variable. So it's handy diagnostic tool to help with variable selection in some cases, such as here. If I were to graph all these, I would be like, well, x2 clearly seems like something we should be including in our model, but that's not ruling out the fact that x1, x3, and x4 may be related to y in some case, and we just can't see it visually in this case. Okay, so now let's run this example. So we're going to make a model, and here we're going to run it against all 4 variables. Okay. So this is a linear fit, exactly the same as before with our univariate model, except now we are adding in a couple other variables. So you basically just, this is the structure for doing a multivariate. It's the same as the univariate, except you add your variables explicitly like this. I can run this model. and look at the summary. Yes. Okay. So there's a question. So a relationship can be significant if we don't see it visually, and we should keep it in the model. Yeah, absolutely. So this whole point of plotting this is part of our initial exploration of the data, is to look at the visual sort of relationship between each of my variables and the outcome that I'm interested in, x1, x2, x3, x4. And sometimes you're actually able to see the relationship very clearly, but sometimes you're not. Okay. And so this is a first step at being able to identify variables that you think are important, but it should not be the thing that excludes variables, because you can have relationships that you don't see visually. So exactly. And in this case, had I only included x2 because I looked at this and said, oh, okay, there's only this, there's only, it looks like this is the only thing that has a relationship, I'm going to be missing out on a real effect, and it's an effect that we know is real. So if we look at the results of our regression, the regression model is actually going to be able to do a nice sort of identification of the relationship. Even if we couldn't see it visually, the math is like there for it to figure it out, right? So we know the true value of x2 is 2, so 1.986, which is pretty darn close, and then x1 is 0.5. One thing to note is that, okay, so we've also included x3 and x4, which we know don't have a real relationship with the true model, right? And in fact, that's what we see here. Neither of these two are significant, which is essentially meaning that the coefficients that are estimated from this model, so 0.057 and negative 0.02, we don't have a good reason to believe that those coefficients aren't different from 0. That's what our standard errors are telling us. So kind of thumbs up, right? This is what we wanted to get from our model, and in fact, it's telling us essentially kind of the right answer. And so that's the example of the multivariate. But when we sort of go down our list of diagnostics, I also want to show another example really quick. So what happens if we only do a regression on the variables that we know are part of the model? And so let's see. So in this case, this in theory should be kind of a better model than this one, which is including extraneous variables, which may be sort of influencing in slightly in a worse way. Let's see. So here we get similar results. Both of the real variables are statistically significant. They're close to the true values that we were hoping to observe, right? They're slightly different because we've introduced some random term, random error. But I want you to pay close attention to one of the diagnostic measures, one of the more common diagnostic measures, which is the R-squared. So in this case, our R-squared is 0.9931, And this is the model that's describing the true model, right? This is x1 and x2, and that's it, and we know that that's the real one. But if I go up to the one where we're including extraneous variables, in fact, you're going to see that there's a slightly higher r squared. Okay, so why the heck is that happening, right? We know that technically this model is better. So it turns out if you go back to the equation on r squared, you are able to explain more variance by having more degrees of freedom. And so essentially what that means is that as I add more variables into my model, my r squared is always going to improve. So let's see, what's the best way to sort of visualize this? If you are, let me see, if I increase the degrees of freedom, suppose that I'm starting in a plot like this, and I only have two axes with which I draw a line through. You can imagine, so if this is x1 and y, you can imagine that if I were to include a new a new variable, I now have an extra degree of freedom to sort of play with, which means that I can get slightly closer to the true y values, or I can, sorry, not the true y values. I can have another parameter with which to explain the variation in my x's. And as I introduce more and more dimensions, I can explain more of the variation in my x's, even if there isn't like a real relationship between the explanatory variable and your response variable, which is exactly what we're seeing here. So if I were to make 100 more random variables that have nothing to do at all with y, because the y relationship with x1 and x2 stay the same. In fact, I will progressively see my r squared getting higher and higher and closer to 1. And that's an artifact of how the r squared is essentially defined. However, there is a term called the adjusted r squared. And so let's take a look at that. So the adjusted r squared in this model with the extra x3 and x4 is 0.9931. And the adjusted r squared, oh, that's unfortunate. It's still, it's still slightly lower. So the adjusted r squared here, you'll also notice that the difference is smaller. The adjusted r squared identifies this specific issue with the way that the r squared is defined. And it introduces essentially a sort of penalty function, so that if I add more and more variables, it's actually going to adjust my r squared downwards. And so now you have some kind of metric that will be able to balance out adding more variables and sort of getting a better model. And so in theory, your adjusted r squared is going to be a nice sort of metric that balances out the additional parameters with the accuracy of your model. And so that general concept is actually going to play a really important role in a lot of the diagnostics that we're going to do. So just keep in mind, we'll talk about adjusted R squared a little bit more sort of later on in the course.
Hey, Alan.
Yep.
So if the R squared formula is like the difference in our observed values with like the regression value squared over the difference between the observed and mean values squared, like
Yep.
why wouldn't you have an R squared value for each variable?
Yeah. So let's see. So R squared is equal to 1 minus yi minus yi hat sum over I squared divided by sum I of yi minus yi mean squared. Okay, so there's only one value here, right? Because you are summing up over all the i's, so it's not as though, you know, it takes into account all the points, and then the area where your x's are playing a role is in yi hat, which is equal to beta hat I xi. And if it's in a multiple regression, multivariate regression, it would be something like this. Beta I hat 2 of xi, oops, this should be 1, not 2, xi2, something like that, right? So even if you have many variables, they're all going to get condensed down into your fit. So there isn't like a separate R squared for every value. The R squared is specifically with your response variable.
Okay.
Yeah. Okay. Great. So that is our sort of first bit of diving into multivariate regression. The next bit of stuff that we're going to talk about, let me turn this off and go back to our whiteboard, are different types of variables. So everything that we've been talking about thus far has been with our explanatory variables being continuous, but they don't necessarily have to be, okay? And so, so we have dummy and categorical variables. And so this is, this concept is how we would deal with non-continuous variables. And so a dummy variable, for example, is a variable with only 1 or 0 to indicate an outcome. And examples of dummy variables, so this could be like heads or tails on a coin, and or let's talk a little bit more realistically about data you might actually see as being dummy. So this might be like male or female, or in like election data set you might have Democrat or Republican, or if you were looking at I don't know, like a coronavirus data set, it might be, you know, 0 if you're healthy and 1 if you're sick. So there are lots of reasons why you would want to be able to handle data that would look like this. And then you also have categorical. And so this is a variable that can take a number of different fixed values. And so this could be, so in the same vein, okay, actually, so let me just write this down. So in this case, this was, what did we say? Gender, party affiliation, etc. Here you might have something like, if we go in the same vein as demographics, education level, it could be race, ethnicity, and so on and so forth. Okay, so let's think about examples of these in R, and I think this is kind of the best way to help learn about this, and the interpretation of these variables is really to do sort of a hands-on look, so that you can get a practical interpretation of how these things work. Okay, so application of dummy and categorical variables. So I'm going to read in a data set called wages. Let me make sure that it's in here. Yep. Oh, I don't have data tables loaded. Okay. So let's take a quick peek at what is in our wages data set. So we have earnings, and these are actually organized for each individual. So this person makes this amount of money, has a height of 73 inches, as a male, white. Education is ED, and age 49. You can see the data types here. Okay, so one of the immediate things to note is that we have a couple numeric variables, integer, which we'll also just kind of call numeric, but we also have these character variables. So what does that even mean to be able to run this in a regression, and what's sort of going on behind the scenes? So let us create a model. So what I'm going to do is run a regression that looks something like this. So y is a function of beta 1. Oh, actually, I should just say, so we'll just call it earnings, is a function of beta 1 times my education plus beta 2 times age plus a set of betas for gender. And we'll talk a little bit more about how this is structured in just a moment. But I think it'll be easier to sort of start with the interpretation. So we'll do a model. It'll be called the wage model, linear, regressing earnings on education plus age plus. So I'm just going to put this for now, and I'll explain this in a second. Essentially, we're going to be adding another variable called sex for gender, and we're getting all this from our wages data set. Okay. So let's first go about interpretation of our model. We're not going to do any sort of diagnostics for now. We're mainly going to focus on interpretation of the dummy and categorical variables. So here, if I go through and look at the betas and coefficients, let's walk through our interpretation. So earnings, which is how much I make a year, is influenced by how old I am and how much education I have. Notice that there's this big intercept at negative 48,000, or about 48,000. What does that mean? So it's essentially saying, so I'm going to ignore this gender thing for now, but it's basically saying, you know, if I had 0 years of education and my age is 0, then I'm starting with a salary of negative 48,000. So that is a bit of a nonsensical number, but it's there because that's essentially where my y line intercepts with, where my fit line intercepts with the y axis. One of the things to note is that you typically never want to extend your fit to bounds that are outside of your data. And so the lowest age that we have is 22, and the minimum education that we have is 3 years. So you know, this number is probably pretty nonsensical because you're far past your boundary. But say I had 15 years of education and I were 30 years old. Then it would be, you know, 30 times this number, or sorry, 30 times my age plus, you know, the 15 years of education times this number minus this number will give you the estimate of your earnings. Okay, so now we've got something a little bit different going on here. This is our dummy variable of male versus female. And so what is going on here? Why does it say male here? So this is describing in our data set the average effect of being a male means that you on average make $21,000 more. And that's after you control for age and education. So the way that R is handling this is that if you recall for how we actually calculate the coefficients, you are minimizing the square distance between my predicted values and the location of the actual education as it relates to earnings and age as it relates to earnings. But then what does it mean for a factor? Because like male and female isn't something that you can like plot on your data. And so here, when I say factor, it's essentially creating a hidden set of extra data. And what that looks like is you're going to have, I think the best way to visualize this is you're going to have two new columns. You're going to have male column and a female column, and then there's going to be ones and zeros here. And actually, I can actually go ahead and create that just so that we can see what this looks like visually. So in wages, I'm just going to quickly make a column called male, and that's equal to when sex is equal to male. And then I'm going to create a column called female, which is when sex is equal to female. Right. So you have true for male, or 1 for male, 0 for female, and 0 for female, or 0 for when in the female column when the sex is male, and true for when the sex is female. And when let's see, when I interpret this, what you end up seeing is something like this. So if we have earnings on the y-axis and we have education on our x-axis, the data might look something like this. And you can have 2 lines with identical slopes, right? So these slopes are both beta for education, but then you now have separate sets of intersects, and those intersects are here. So this would be negative 47,907, and then here, and so that would be for a female, and here this is negative 47,907 plus the 21,000, and that would be for a male. So when you have a dummy variable, or in fact a categorical variable, it's essentially doing the same thing. You are creating multiple intercepts for your lines. And the one thing that's oftentimes a little bit confusing and misinterpreted, especially when you're first learning about this, is that when I have a category of 2 or more, so dummy is essentially a categorical variable with 2 discrete outcomes. You always end up omitting one outcome, and that is your base level. So whatever is not included here is in your base intercept. And you add everything on top of that to do the interpretation for the other categories. Okay, So we are basically out of time for today. So I will come back to start off on this topic at the beginning of lecture next time. Okay, and other than that, just make sure to have your homework submitted by the end of the day today. And we can end here, and I'll stick around a couple minutes for answering any questions people have.
Hi, Alan.
Hey.
I have like some question regarding the homework.
Okay, yeah. Oh, 1 sec. I'm gonna stop the recording.